Hey guys, welcome to a new lesson. This is lesson 9.3.1, graphing linear two-variable inequalities. In section 9.2, you learned how to use an inequality with one variable to help solve a word problem. You also discovered that a one-variable inequality can have 0, 1, or more solutions, and that these solutions can be represented on a number line. But what if the inequality has two variables? So instead of just x and y. What is the solution to a two-variable inequality? How could these solutions be represented graphically? That is what we are going to find out today. 9-65, examining the solutions of a linear equation. Find your graph of y equals negative 2x plus 3. I found it. Here's my graph. Y equals negative 2x plus 3. This is in slope-intercept form, meaning it's in y equals mx plus b form. And I want to remind you that anytime you have an equation in this form, we're going to see this later again, so it's useful to go over it. M is your slope and b is your y-intercept, okay? All right, part A says, is the point negative 1, 5 a solution to the equation y equals negative 2x plus 3? How can you tell by looking at the graph? How can you tell by using the equation? So there are three questions here. Is the point negative 1, 5 a solution? Well, how can you tell by looking at the graph? Let's see if this point, negative 1, 5, falls on the graph of y equals negative 2x plus 3. Meaning, does negative 1, 5 fall on the line? Let's see. Negative 1, 5 is here. And yes, it does fall on the line, meaning that it is a solution to this equation. Okay? So, yes, this is a solution. Because the point negative 1, 5 is on the line. But there was also another part to this equation. How can you tell by using the equation? So how can you use y equals negative 2x plus 3 to figure out if negative 1, 5 is a solution? Well, here they're giving you an xy coordinate, and so why don't we plug in negative 1 for x and 5 for y to see if this makes the equation true. And if it does make the equation true, then we know that it is a solution. So plug in 5 for y and plug in negative 1 for x. Again, I'm just getting that from this point. This is 2. 2 plus 3 is 5. 5 equals 5. This works. So not only is negative 1, 5 a solution because it falls on the line, but also it makes the equation true. So overall, yes, negative 1, 5 is a solution because the point negative 1, 5 is on the line, and it makes the equation true when plugged in. Part B says, is the point 2, negative 1 a solution? What about the point 0, 0? Justify each conclusion with both the graph and the equation. So let's take both of these points and let's see if they're on the line. If they're on the line, they're a solution. If they're not on the line, they're not. And then let's plug them into the equation to see if it makes the equation true. So the point 2, negative 1 is here. This is on the line, so this is a solution. Okay, let me write solution here too, since I didn't before. 0, 0 is right here. This is not on the line, so this is not a solution. Let's verify that 2, negative 1 is a solution and 0, 0 isn't by now plugging these values into the equation. y equals negative 2x plus 3. So here I'm going to plug in negative 1 for y, again, because this is an xy coordinate. And I'm going to plug in 2 for x. Let's see, negative 1 equals negative 4 plus 3. Negative 4 plus 3 is negative 1. That works. So we can tell from the equation that this is a solution. We already knew that from the graph, but now we're confirming. Let's confirm that 0, 0 is not a solution. So take your original equation, plug in 0 for x and 0 for y. Again, we're getting an xy coordinate, so that's why we're getting those values for x and y. Let's see, here 0 does not equal 3, and so this is not a solution. We already knew that, but now we're confirming. Okay. Last but not least, let's answer part C. What determines if a point lies on the line? What is the difference between the points on the line and the points not on the line? So as you can see, if a point lies on the line, it's a solution to the equation because it makes the equation true. So let's write that. All points on the line make the equation true. And that is it. Let's see how this is applicable for inequalities. 9-66, graphing a linear two-variable inequality. In problem 9-65, you found that the points on the line are the only points that make the equation y equals negative 2x plus 3 true. But what if you want to graph the solutions for the inequality y is greater than or equal to negative 2x plus 3? How will that graph differ from the graph of y equals negative 2x plus 3? Let's test some points. So big difference. We're dealing with greater than or equal to, not equals in this case. So here, test the following points. If the point makes the inequality true, plot it on the graph. So the way that I'm going to test the points is by plugging it into the original inequality, and if it works, then I'm going to graph it. So here's the original inequality. Y is greater than or equal to negative 2x plus 3. So one at a time, I'm going to plug these points in, and again, if it works, if it's true, I'm going to plot it on the graph. So first, let's plug in negative 1, comma 5. So always x first and then y. So 5 is greater than or equal to negative 2 times negative 1 plus 3. Negative 2 times negative 1 is positive 2, and then 2 plus 3 is 5. 5 is greater than or equal to 5 because we have that or equal to piece. So this works, which means that we can graph negative 1 comma 5. This is a solution. Let's plot that point, negative 1 comma 5, right there. Now let's try 2 comma negative 1. You'll notice that the first 3 points are the same ones as we saw before in the previous problem. So I'm going to plug in negative 1 for y, 2 for x. This is negative 4 plus 3, which simplifies to -1. -1 is greater than or equal to -1 because of that or equal to part. So this is a solution, and I'm going to graph that point, which is right here. Let me label these points as I'm graphing. -1, 5, 2, -1. Now let's plug in 0, 0. Zero is not greater than or equal to 3, so not a solution, which means I'm not going to graph it. I'm not going to draw that point. Let's try 0, 7 now. So we're going to plug in 0 for x and 7 for y. Let's simplify. Is 7 greater than or equal to 3? It is, and so this is a solution. So we're going to plot that point, 0, 7. That's right here. 2 more points to go, and as I do these last 2 points, this is what we're doing right now is actually a modification of what the activity actually looks like when you do it straight from the CPM book. Everyone gets a point to test, and everyone gets a little sticky dot, and if your point works, you put it on the class graph. And I enjoy those types of activities because it provides a really good visual representation, but this will have to do. Okay, let's see, that is -6. Is 4 greater than or equal to -3? It is. So this is a solution. We're going to graph this point. 3, 4 is right here. One more. Let's plug in the point. I need a different color now. -2, 3. So plug in -2 for x, 3 for y. Simplify. This is not true. 3 is not greater than or equal to 7, so this is not a solution. So I'm not going to draw this point. So hopefully you can see here that we have points on the line that do make the inequality true. We have some points to the right of the line that do make the inequality true. What I'm going to do now is I'm going to go to the Desmos site, and right now I have y equals -2x plus 3 graphed. Let's see what happens if we graph y is greater than or equal to -2x plus 3. Here you'll see that the whole right side of the line is shaded, which means that all of the points to the right of the line are solutions. So I could keep going with what I was doing before, and what I would find is that all points above the line make the inequality true, and when all points make something true, I can just shade in that direction. So kind of similar to shading like on a number line, except now we're shading a whole graph on one side. So some key points. All points above to the right of, because it's like above, but it's to the right of the line, make the inequality true. So these are solutions. Oops. I forget I can't write super close to the screen because the computer gets mad at me. Not only are all of the points above the line solutions, but all points on the line are solutions, and we can see this because we had -1, 5 and 2, -1 that make the inequality true as well, so we can assume that all points make this inequality true. Because we're shading all of these points, there are infinitely many solutions. And that is it. Okay. For this specific example, no points below the line make the inequality true. Okay, we saw this in 0, 0 and -2, 3. Both of those points are here and here. They're below the line, they don't work. So in this case, all of our solutions are above the line. So this is how you graph a 2-variable inequality. Before we were doing number lines, and now we're doing full graphs. So let's move on to the next problem. What else can you learn about solutions of linear inequalities? Think about this as you answer the questions below. Part A says, what if the graph were shaded like the one at right? One inequality would correspond with this graph. Okay, if you notice, this is the same line. This is also y equals -2x plus 3 because we have a y-intercept of 3 and a slope of -2. But notice that here, for our problem 9-66, we shaded above, so it was greater than or equal to. Here we're shading below, and so how would the symbol change? Well, now it would be y is less than or equal to -2x plus 3. Again, that is because we are shading below. So our inequality symbol is changing. So we've answered part A. Part B says, Heidi asks, what if I changed the inequality to be y is less than -2x plus 3? Now what would the graph look like? Discuss this and decide the best way to represent the solutions to the inequality y is less than -2x plus 3. So what would change? If I'm going from less than or equal to strictly less than, how would that change the graph? Well, let's see. Let's see if Desmos can tell us. So now instead of y is greater than or equal to -2x plus 3, I'm going to graph y is greater than -2x plus 3. What do you notice? What's different about using strictly greater than or using greater than or equal to? I know the problem wanted less than and less than or equal to, but I want you to notice a key difference. Notice that for greater than or equal to, this line is solid. As soon as we change from greater than or equal to strictly greater than, it's a dashed line now instead of a solid line. So we can assume that the same is going to be true for this problem. Okay, if I want less than instead of less than or equal to, what that's going to do is that's going to make this line dashed instead of a solid line. So I can write here, changing the inequality symbol from less than or equal to less than would make the line dashed. Here's why, because if you try to plug in values, now any point that's on the line is not going to be a solution. Okay? If I take, let's see, we've tried to plug in 2 comma -1, and it makes the equation true. If you try to plug it into this new inequality with just strictly less than, it's not going to be true anymore, because once you lose that or equal to part, you lose all of the solutions that fall on the line. Okay, so I'm going to add here, changing the inequality symbol from less than or equal to less than would make the line dashed, because the points on the line are no longer solutions. So this kind of corresponds to the open circle and the closed circle before. For previous lessons, less than or greater than would give you an open circle on the number line, and less than or equal to, greater than or equal to would give you a closed circle. Right? Now, what I'm saying is that when you graph these lines, less than, greater than will give you a dashed or dotted line, okay, as long as it's not a solid line, and less than or equal to, greater than or equal to will be a solid line. Okay, please let me know if you have any questions regarding this. Our last problem for today is to practice graphing these linear inequalities. So for each inequality, graph the boundary as either a solid or a dashed line, and then shade the region that makes the inequality true. So this right here, greater than, means that this is going to be a dashed line. What line are we going to graph? We're going to graph y equals -1/3 x minus 1, and I told you a little earlier in the video that anytime you have a linear equation, your m is your slope and your b is your y-intercept. So if I want to graph this line, my y-intercept is at -1, my slope is at -1/3, so I'm going to go, if I make a slope triangle, I'm going to go down 1/3 and down 1/3, and I can draw a straight line. Let's see. But remember, it's got to be dashed, because we said it was going to be dashed. It can't be a solid line. So there we go. There's our dashed line. Again, I used this as my slope, and that is my y-intercept. Now, which way do I shade? Do I shade above the line or do I shade below the line? Let's test a point and see. Just like the number lines where you would test a point on either side of your boundary point to see which direction we're going to shade, we can do that here too. Pick a coordinate point above the line and then pick a coordinate point below the line, and whichever point makes the inequality true is the direction that you're going to shade. So here I'm going to test, let's pick an easier point, 0, 4. Let's test that. So my original inequality is y is greater than negative 1/3 x minus 1. Oops. Plug in 4 for y. Plug in, let me pick a color so you can see me plugging this in. 4, 0, 1. Again, I'm testing 0, 4. So I'm plugging in 0 for x, 4 for y. Is 4 greater than negative 1? Yes, it is. That is great news. That means that we're going to shade above the line. Let's double check that a point below does not work. Let's test 0, negative 3. So here's my original inequality. Plug in negative 3 for y and plug in 0 for x. Is negative 3 greater than negative 1? Nope. So we're not going to shade in that direction. All my solutions are above the line. Okay. Let's do part B now. Because we have less than or equal to, that's going to be, refer to this, you should write this down somewhere. This is going to be a solid line. So when we draw our lines, there's not going to be any breaks. For this inequality, 4 is our slope, 2 is our y-intercept. So starting at 2, I'm going to draw my slope triangle. I'm going to go up 4 and over 1, and up 4 and over 1, and I'm going to draw my line. I have this ruler tool so I can draw a straight line. Okay, solid line. Now, just like before, test a point on either side of the line to see which direction you're going to shade in. So let's test negative 3, 0, and then let's test 2, 0. And whichever point makes the inequality true determines the direction in which you're going to shade. So here's that original inequality. Plug in negative 3 for x and 0 for y. So 0 is less than or equal to 4 times negative 3 plus 2. 4 times negative 3 is negative 12, and negative 12 plus 2 is negative 10. Is 0 less than or equal to 10? No. So I can already tell you that we're not going to shade to the left. We're going to shade to the right. Let's confirm. Here's my original inequality. Plug in 2 for x, 0 for y. Let's see. 4 times 2 is 8. 8 plus 2 is 10. Is 0 less than or equal to 10? Yes. That works, which means that we are going to shade in this direction. Everything to the right of the line. Okay, 2 more to go. Okay, here we know this is going to be a dashed line. Here's my slope. Here's my y-intercept. Starting at 3. My y-intercept, I'm going to draw a slope triangle. Your slope, is always rise over run. So if our slope is 5/2, I'm gonna rise 5 and run 2. And let's draw my line. Again, we said dashed line, and so make sure you dash the line when you draw it, or dot. That is okay too. I'll do dotted this time. Okay. Now let's figure out which direction to shade in. Let's just test 1 point to the right and 1 point to the left, and then we'll see which direction we're going to shade in. So I'm going to test. I like testing coordinates that have 0 in them because they're pretty easy. So let's test 0, 0. And let's test, let's do 0, 8, because that's to the left. Yeah. Okay, let's do it. Here's my original inequality. So 0 for y and 0 for x. Simplifying, you get 0 is less than 3. Is this true? It is, which means that this is a solution, which means we are going to shade in this direction. Okay, that's it. I know I don't, let's be thorough. I'm getting a little tired and I don't want to test 0, 8 to make sure it's not a solution to show you, but it's always good to be thorough. So let's just make sure that 0, 8 doesn't work to verify that we shouldn't be shading in that direction. So here's my original inequality again. Plug in 8 for y, and then plug in 0 for x. You simplify, you get this. Is 8 less than 3? No. So we don't shade in the direction. So we were correct. I hope you're starting to get the hang of this. And if you're still watching and hearing my voice, I appreciate you sticking around. Thank you for your hard work and effort. Okay, part D. First of all, this isn't in slope-intercept form, so let's subtract let's rewrite this so that we get y by itself. So subtract 2x from both sides. And this is a perfect time to remind you that when we divide by a negative, or when you multiply by a -2, you've got to flip the sign. So because I want a positive y, I want y by itself, I don't want negative y, I want positive y, I need to divide everything by -1, which means that instead of having less than or equal to, now I have greater than or equal to. Okay? I believe I wrote that in the previous video. Okay, so then that would be 2x and -5 now. So this is the inequality that we're going to graph. Because we have greater than or equal to, this is going to be a solid line. Here's our slope. Here's our y-intercept. So let's graph. -5 is our y-intercept, and my slope is 2, so if I drop slope triangle, I would be going up 2 and over 1. And up 2 and over 1. Up 2 over 1. Get out my ruler, draw the line. Okay, let's figure out what direction to shade in. 0, 0 is a pretty easy point to test, so let's test that. Here was that inequality again. -5. And we're testing 0, 0. So I'm going to plug in 0 for y, and I'm going to plug in 0 for x. And if this works, then I'm going to shade towards 0, 0. Is 0 greater than or equal to -5? It is. Thank goodness. That means I'm going to shade in this direction. Everything to the... I can't highlight correctly inside the line. Let me do this instead. It's always so messy. I have everything in this direction. So there you have it. We leveled up. We went from solving inequalities with just x and drawing number lines to now solving inequalities with x and y and drawing graphs of lines and testing points still and shading still. But now it's a little bit more complex. I really wish we were still in the classroom because this is, I would love to have done the activity for this lesson in person and to be able to answer questions in real time. But please know that if you have any questions about the material, I'm one click away. Email me, okay? Have a great day.